This is the Tech Talk for phase-sensitive innovations. This Tech Talk will focus on enabling technologies for agile wideband radio frequency imaging systems. Who are we? We are a small technology business based out of Newark, Delaware, located in the Northeast Corridor, the second largest megalopolis in the United States in terms of population and the largest in terms of economic output. We are close to the University of Delaware and perform some of our fabrication efforts there. We have a Class 100 and a Class 1000 cleanroom, and we are in the process of adding a new building. We currently have a wide array of expertise that covers thin film lithium neobate, including our own manufacturing facilities, photonic integrated circuits, also known as PICs, RF engineering, and RF photonic systems engineering. The warfare environment is rapidly changing, with modern military environments including a wide variety of electronic signals. RF spectrum coverage is expanding with the advent of 5G, and future RF systems need to be capable of employing said bands. The ability for RF systems to monitor, identify, track, and communicate with a variety of signal types across an extremely wide range of frequencies has never been more critical. More specifically, when considering several RF application examples, one can see a common set of requirements for modern RF systems, including high gain beams in multiple directions, low power processing of that beam space, wide band frequency coverage, and low latency. PSI's core technology employs optical techniques for RF system processing to deliver on all these requirements. In subsequent slides, we present an example of one of our RF photonic systems to illustrate how this is all possible. Our RF photonic systems can be thought of as RF imaging systems. They literally provide the ability to see RF signals in much the same way as traditional optical imaging systems allow us to see at visible or infrared wavelengths. To image RF signals, you must be able to simultaneously process many RF beams in real time, as illustrated in the upper right graphic of this slide. It is our use of optical techniques that enables this capability in our RF photonic systems. In the bottom half of the slide, we show an example system that consists of a Lundberg lens, which images incoming radio waves. At the back side of the lens, we have an array of RF to optical conversion modules to pick up the imaged RF signals. The signals are subsequently routed with optical fibers to an array of photodetectors where they can be down-converted and detected simultaneously. Although this is an example of a receiving system, we can also generate and transmit RF signals by swapping the locations of the RF to optical conversion modules and the photodetectors. On this slide, we show another illustration of the RF imaging system using photonics. The photonic elements employed on the back end are effectively agnostic to the RF frequency because large RF frequency ranges, such as 1 to 100 gigahertz, is an extremely small fraction of the optical frequency, so the photonic components do not exhibit large variation over these ranges. Transmission of the signals over optical fiber provides low loss and low latency as compared to traditional RF cables, especially as frequencies increase. At the optical output, the photonic backend offers direct down conversion to lower frequencies, which enables the use of lower-cost electronics for processing, as well as higher effective number of bit analog to digital converters. The Navy programs we are currently executing are focused on the development of photonic integrated circuits, or PICs, which can be considered as key enabling technologies in the implementation of RF photonic imaging systems. PICs offer the capability to integrate a variety of photonic components and functionality into singular chips, much in the same way as traditional integrated circuits or RF integrated circuits. As such, PICs result in significant reductions in the RF photonic system size, weight, power, and cost as compared to traditional discrete photonic components. Our PIC development requires design, integration, packaging, and testing over several iterations with key enabling PIC technologies available within the next few years. We show an example of the potential form factor reduction that can be achieved with the implementation of PICs, a traditional discrete optical component RF processor that is roughly 12 inches on a side, can be condensed into a package that is less than 2 inches on a side. A transition to a Phase 3 program requires integrating PIC-based technologies into existing systems and testing those systems. These efforts will allow us to approach the commercial market with performance metrics of our systems to demonstrate the value added by the PIC implementation. Commercial markets of interest for our RF photonic systems include SATCOM, as well as 5G and 6G wireless. With regards to transition opportunities, we are interested in providing these systems to DoD primes for integration onto all platform types, such as air, sea, and land. Secondarily, we can provide access to our enabling technologies at the component level to RF solution enterprises, which we perceive to be a value add for those enterprises. We are Phase Sensitive Innovations, a research and development company based out of Newark, Delaware, who specialize in RF photonic systems, lithium niobate wafer processing, and photonic integrated circuit development. We are developing RF beam-forming systems using optics and plan on leveraging our expertise in photonic integrated circuit technology to develop lower SWaP-C RF imaging systems. The technical points of contact are Dr. Timothy Criazzo and Chase Stein. The business development point of contact is Dr. Ahmed Sharkawi. Please contact us if you would like to discuss our technology further. Thank you for your time.